Whenever we multiply two numbers or functions, say x and y, we normally take for granted the commutative property. That is, we take for granted that we're going to have the condition that if I multiply x times y, that's just going to be equal to the same thing as multiplying y times x. Or if I have two functions, f of x and g of x, that it doesn't really matter which order I place those functions, their product will give me the same result. Okay, this is something that is common to many algebra systems. However, when we come to operators, we have a very different sort of situation possible, because the operators are transforming functions into different functions. So it is not necessarily true that the order would be immaterial. Now, if I were looking at two numbers and I wanted to test whether they obeyed the commutative property, one way I could do that would be to simply take the difference between the two possible orders and test to see if it gave me 0. If it gives me 0, then they commute, or they obey the commutative property. So I can do something similar if I have a pair of operators. So for example, I might take a pair of operators, A and B, and simply subtract what they give when they're in the opposite order. Now, ordinarily, we need to operate the operators on something. So let's assume that we're operating these on some function, some wave function psi. So really what we're trying to evaluate is this kind of quantity, okay, because bringing the psi outside that doesn't change the value of this. So what I want to do is figure out what is the impact of taking this combination of operators, A operating then, or A and then B operating, or B then A operating, and what does this give me as different results. So I can anticipate that there will be two extreme possibilities. In one case, I'll get 0, just as I do for numbers. And in this case, we would say that the operators commute. That is, they have the ability to be interchanged no matter which way I want to interchange them in applying these operations. But I also could have the situation where they don't equal to 0 when I do this. And in that case, I would have the case that operators do not commute. Now, at this point, I understand that you're probably a little unsettled by the fact that you would have to pay attention to what order these operators go in, but it turns out there's more importance to this than we think, because it turns out the relative commutation properties of two operators has something to say about their eigenfunctions. Okay, let's see if we can illustrate that. So what I'm going to do is I'm going to assume that I have a set of functions. I'll call them psi of n, and psi of n, it turns out, will be eigenfunctions for two different operators. So I'll say for both A and B. And so now what I want to see is how would this influence the outcome of a commutator. Now what I'll do is I'll define these operations. So A operating on psi of n will give me an eigenvalue A sub n. B is a different operator, so I'm going to expect those eigenvalues to be different eigenvalues. So I'll write this way. And I'll basically stipulate that A sub n and B sub n are not the same numbers. They're different numbers, though the functions, the eigenfunctions, are the same for both of these. All right, so now what would I get if I took the operation of a commutator and applied it to one of these functions? Well, I think it's pretty straightforward to see that what I'm going to get is I'll have A times B operating on this function, which will give me little b sub n times that function. And then I'll have minus B operating on A operating on that function, which gives me little a times that function. But B won't have any impact on a number, nor will A, so I can bring those numbers out front. And continue with that operation. So I'll end up with b sub n. A operating on this will give me a sub n, and I'll get the function. And here I'll have a sub n. When b operates on the function, I'll get b sub n. And since these are numbers, and this is the same function, I think it's pretty easy to see that the result here should be 0. So in other words, when I apply this combination of operators to a set of functions that are eigenfunctions of both of those operators, I should get 0. Now, it will turn out that we can, and I've talked about this in an earlier video, we can express almost any function as a linear combination of the eigenfunctions of a Hermitian operator. So, in other words, if I can express any function as an expansion in these functions, where these coefficients are just numbers here, then if I apply this same operation to this set of functions, like this, it turns out I can insert this operation in the middle here for each one of these terms. So I'll have a sum of terms where I've got a, b, minus b, a, operating on this eigenfunction psi n. But I've already shown up here that that's going to give me 0. So for each and every one of these terms, I've got this thing that equals 0. So I've got a sum of terms of all zeros, so the whole thing as a whole must be 0. So what this demonstrates for us is that this combination of operators, if they share the same set of eigenfunctions, and I can write any arbitrary function as a linear combination of those eigenfunctions, that I will always get 0 when I make this operator combination. Well, there's a shorthand way, of course, of writing this down. We take this this set of operators and we can write it in square brackets as a, b. So this is defined as this combination of operators. And now we have the very important tool in our toolkit that when this commutator turns out to be 0, that means that a and b share eigenstates or eigenfunctions. All right, and this is going to turn out to be a very important property because it tells us something about how well we can precisely measure simultaneously the properties that A and B happen to measure for a given system.